maximizing submodular functions in streaming settings. Okay, so the definition we've seen so many times now. Submodular functions exhibit diminishing returns. In particular, I'm going to use this notation a lot for the marginal value, where f sub s of e will denote the marginal gain of adding e to s. Okay? Okay, good. And within that submodular functions, I'm going to talk about monotone functions and non-negative functions. Okay, nothing new. Okay, so the basic example of monotone submodular functions to me is just coverage. Here are some sets over points. If I take some subsets, my score is the number of points I cover, right? As far as submodularity goes, let's focus on this set first. It covers 4 points. And if I had already covered that point, my gain is down to 3, right? Similarly, if I had covered these 2 sets, my gain is down to 1. All right, so obviously we spent all week talking about this. So my non-negative example is going to be directed edge cuts. So here I take a subset of vertices, and I get points depending on the number of arcs that leave my vertex set, right? So in particular, there's some arcs between red vertices. I don't get points for that, right? Just to quickly go over the submodular part. If we look at this purple guy on the left, he's worth 3 initially. If I put my cut back, he's only worth 1, right? But at least that example is still monotone. So if I instead look at something up near the top left, okay, he's worth 2. And if I put that red set back, now I'm actually losing an arc that I had before. And those other 2 don't get me points either. Okay? So that's going to be my running examples. Good. So kind of the general problem in a monotone or non-negative setting, I want to take k elements and try to maximize the score. Okay? And of course, k elements can be extended to more fancy things like matroids or intersection of matroids. Okay, good. So so this talk is going to be concerned with a very particular kind of streaming model. We heard a different model. Oh, yeah?
We want to pick k elements or at most k elements?
At most k, yeah. We're not going to try to get bases. It is important. Okay. And right, so we just heard one online model, which was the secretary model. And I think there's going to be some distributive models later this week. But in this model, the elements are going to be presented to me one at a time in a stream. Okay? In arbitrary order, not random order. And really, at a high level, I'm just thinking about having space in proportional to my output size, and completely independent of the size of the stream. Okay, so k polylog k is fine. Even polynomial in k would kind of fit the high-level scheme, but nothing we see will take advantage of that. Okay, so this is the model. And I'm also going to just assume oracles. I'm going to have an oracle for evaluating f. And when we get into more sophisticated combinatorial constraints, I'm also going to have an independence oracle. Okay, so we're just going to abstract out any such implementation details. Okay, good. Okay, so in the monotone regime in streams, for the cardinality constraint, the best approximation ratio is 1/2 minus epsilon by BD et al. From their KDD paper. Okay. For more general constraints, such as matroids, matchings, matroid intersection, Chakrabarty and Kale have about a 1/4p approximation ratio for the intersection of p matroids. Okay, the space is a little different. The first paper used k log k over epsilon, and here they use k space. Okay? All right, so in this paper, my co-authors and I were interested in extending these algorithms to the non-negative setting. Okay, so the first of these results, for a cardinality constraint, we get an approximation ratio of 1 minus epsilon over 2 plus e. Okay? And the space has gone up a little bit by a factor of epsilon. For more general combinatorial constraints, we get up to a P matroid, and we get an approximation ratio of about 1 over P. It's a little messier than that. Okay?
So this is more general than the previous algorithm?
This is non-monotone, just non-negative. We're giving up monotonicity, sorry. So I tend to use non-negative kind of synonymously with non-monotone. Okay. That's a big deal. Okay. All right, so fine. So just to see how the ratios go down a bit in one view, 1/2 goes down to 1 over 2 plus, that should be an E, not epsilon, I'm sorry. And 1 over 4p goes down to about 1 over 5p. Okay? It doesn't really matter. Okay, so I see roughly all the algorithms so far as kind of extensions of the greedy algorithm. And so I'm going to try to present it as such. Yeah?
So could you go back?
Uh-huh.
So that 1/2, the best single machine algorithm for it was 1 minus 1 rate. So there is 13% gap. What's the gap for the non-negative that you're presenting here? You're giving 1 over 2 plus E.
That's 1 over 2 plus E. I have a typo.
For the single machine is 1 over E the best approximation?
On the offline? That's right. Offline looks like 1 over E plus 0.004. Yeah. Okay. We'll actually come back to that too. Okay, good. Right. Okay, so right. So I'm going to start from the very basics. Just quickly review the good old-fashioned greedy algorithm, and gradually work our way up, picking up tricks here and there. Okay. So so we know, and it's been said many times this week, that just the basic cardinality constraint, the greedy algorithm is already optimal, right? 1 minus 1 over E. And in case anyone forgot, you know, at each iteration, I just take the element with the best margin. Okay? All right, no big deal. Now moving into some of these streaming algorithms. Okay, so first, you know, when we write these algorithms, we're mostly thinking of, I'm holding some solution S, an element comes, and I have to decide if I want to keep it or get rid of it. In our model, we don't actually have to add him to S right away, although our first couple of algorithms will. So they're more online-ish in this regard. Okay, so for the cardinality constraint, BD et al. Do a thresholding algorithm. So suppose for the moment we actually know what the value of optimum is. They just check to see if the margin is at least opt over 2k. Okay, so certainly if I collect k elements, I've got an opt over 2. Meanwhile, anyone I reject, his margin against me is at most opt over 2k. Okay, so it's delightfully simple. As far as how we guess opt, so here we start taking advantage of some of the streaming model. They're going to run many of these algorithms in parallel based on different guesses of opt. Okay, and we can always estimate opt within a factor of k because of submodularity. All right, and this is where the space goes from k to k log k over epsilon. Okay, so it's a very slick algorithm. Okay. Right. Good. So flowchart will look something, I guess, like this. I reject all the elements as soon as I hit the capacity. Okay, this will be in contrast to our next algorithm. All right. So Chakrabarty and Kale, remember, they're going after slightly more sophisticated constraints like matroids and matchings, where we do some exchanging. So long as we haven't filled up our set yet, they're going to just take everything, because we're in a monotone regime and that can't hurt us. On the other hand, once S is filled up, they're going to look for ways to add the element while keeping S independent. Okay, in the case of cardinality constraint, just look for one guy to delete. Okay, and if they find something that is a quote-unquote good enough exchange, they'll make that exchange, right? And the crux of their algorithm and analysis really lies in what is the accounting necessary to determine good enough to pull out that approximation ratio. Okay, so I guess a flowcharty thingy for this, in contrast, it's all about the exchanges on the right. Okay, so I won't go into exactly how they determine good enough, but we'll see a different measure soon enough anyway. Okay, all right, so those were the two main monotone streaming algorithms that we base our work on. And so now I kind of want to review some basics in the non-negative or non-monotone regime. Okay? So first of all, as we've noticed so many times, greedy doesn't work. I mean, the dumbest reason is that if I set the capacity to at least all the vertices, my algorithm will take everything. Right? And I'll get 0 points. Not too great. Okay. So on the other hand, things that do work look a bit like greedy, okay? And Rico began to explain this pretty well in his questions. So for example, there's an iterated greedy algorithm. It's going to run greedy once, and it runs greedy on the leftover elements, and even does some post-processing work on the first solution. And it pulls out a constant factor loss. Okay, and it's deterministic, just the ratios are much worse. And then more recently, there's a randomized greedy algorithm, which looks a lot like greedy, but injects some randomization. Okay, and that gets a 1/e approximation ratio. You work a little harder, it gets a little better. Okay, right. So I guess to slightly expand upon what Rico said, or at least put it in print. Why is greedy still around if it has unbounded approximation ratio? Because in the analysis, if S is my greedy solution and T is an optimal solution, I can often reach a point that looks like f of S is at least some constant times f of S union T. Okay? Without invoking monotonicity. And it's only in the last step where we actually pull out our final inequality. Okay? So we get pretty far analysis-wise. And from there, so the question becomes what I'm going to do about this guy. And so this might be the lemma maybe underneath Rico's top left box. And this is by Bookbinder and Feldman et al. If I bound the probability of any element being in S by 1/2, then S union T gets me at least 1/2 of T, of f of T. Okay? So this is very wieldy and very nice. So maybe just for sake of completeness, because it wasn't covered yesterday, I just wanted to mention that the randomized greedy is actually quite, I guess, elegant and simple, just nice to see. In each iteration, I instead gather the k elements with the best margin, and I pick one of them randomly. Okay, nothing, but just nice and clean, and it's good to know. Okay, so fine. So I'm finally approaching the part where we actually did our work, which is non-negative maximization in a streaming setting. Okay. So at a high level, I'm going to take everything we've seen, the thresholding and exchanging, and in this kind of sense of randomized buffer, and just mash them all together. Okay, and then we just have to be a little delicate in how we do so. So the algorithm in print looks a little bit more like this. Okay, so I start with the empty solution and an empty buffer. And as each element comes, I try to determine more or less if this element is good. And we'll go into that subroutine in a moment. The main point is that if it is good, rather than adding him directly to my set, I'm going to add him to this buffer. Okay? And only when a buffer fills up do I pick an element out of this buffer randomly. Okay, so this is very similar to the randomized greedy algorithm we saw. Okay, and it's good, of course, doesn't just mean add. It can mean add or exchange as we see fit. And last couple more points. Once I do add an element to S, some of the kind of whether or not the elements in a buffer are good, that's going to change a little bit. So we clean up B, make sure only quote unquote good elements are left. Okay, and then the one last step is at the end of the algorithm, not only do I have my solution S, but I have this buffer B. Okay, and I'm actually going to run an offline algorithm on B and then return the best of two different solutions. Okay, so that's a high level, but the tricky part is figuring out what's good. Okay, so this is kind of simplified for a cardinality case, but nonetheless. So insofar as my set is not full, I'm going to take a thresholding technique like before. Right, I should note this is a little misleading in the sense that I threw up the matroid algorithm, but we're only talking about cardinality. So some things might seem a little excessive, but it keeps things simple. All right, so if my set is all filled up, then I'm going to try to look for a good exchange. And in particular, I'm going to compare the margin to this kind of magical value here. We'll try to figure out how to design this in a moment. Okay, plus an additional threshold. Okay? All right. So what should my magic value kind of eta be like? Right, this is going to tell me what I put into the buffer. First, when I'm trying to extract out the approximation ratio, it really helps if I can kind of account for the value that I originally added to D to S once upon a time. So when we do the written proof, this is a really good thing to keep in mind. The next thing I want eta to satisfy is, as S changes, kind of loosely speaking, the value of its members will go up and down, right? So as I add elements to S, there might be more and more redundancy with D, right? The sort of value, again, loosely speaking, of D goes down. And conversely, when I remove elements from S, D might become worth more, right? So that's one of these things we want to try to balance. And at a high level, I really want to ensure that when I make this exchange, I really take a sizable step on f of S. Okay, and the reason is I also want to limit the number of times I take elements out of the buffer so I can use Bookbinder et al.'s very nice lemma. Okay, and if I'm always taking steps in proportion to opt over k, at some point I'm going to hit opt, and I can't take so many guys out of the buffer. Okay, so that's the strategy. And eventually we settled upon this rather simple definition. Okay, so I take my my solution S, and I'm going to number the elements in the order that I added them to S. And then the incremental value is what we called it for lack of a better name. It's just the margin as we build in this order. Okay. So of course we decided upon this because it makes the proof go through, and we're not going to do the proof, but we can at least do some sanity checks and build some intuition why this is a reasonable measure of value. Okay. So first of all, certainly the moment I add the element, that incremental value is going to should be S minus D plus. Anyway, the incremental value is going to match what was added because it'll be the last element added in that definition. Okay. Maybe another nice property is that when I sum up the incremental values, I regain all of f of S. Right? So other natural definitions, this isn't true because of submodularity. Okay? And a third nice property in our analysis is that the incremental value of a fixed element is only going to go up. Okay? So, it can only go down in a way when I add elements to S, but within our definition, those elements will be appended to the end of the list, and the incremental value won't change. Okay? And on the other hand, it might go up when we remove elements earlier on the list. Okay? Right. So that was just our definition. That's some intuition. Backing back out, so that's how we determine that an element is good. This is the overall algorithm. Okay? That's right. I'm going to pick E in the buffer uniformly at random. Buffer is going to be sized K over epsilon or something. Okay. All right, a lot of this was right, just trying to make this buffer technique work. Okay, good. All right, so I think I'm running out of time anyway. A quick conclusion, the technical result is we get these constant factor approximations in the streaming setting. For a broad class of combinatorial constraints, you can apply Bernoulli's and chase things through. Okay. The algorithm itself, I guess, can kind of be divided into basic components. The main ingredients to me are the randomized buffer. We have greedy, but with respect to this notion of incremental value. And then we also had that post-processing step. Okay? And the open questions, I guess, at a high level, beyond improving ratios, is how to model in general kind of this big data setting and maximization. This is only one of many possible models. And then also, lower bounds. A lot of the lower bounds out there are working in slightly more strict regimes, like very online stuff, okay, without this extra wiggle room of space. Okay, so that's all. Thank you.
Do you think you can adapt this algorithm for, dynamically changing ground sets? So if the ground set grows over time?
Yeah, so this makes no assumption on if the ground set ever ends.
Yeah, but you have to guess opt.
You have to guess, okay, so if roughly I've seen the biggest elements so far, and I know that the rank of the overall system is K, so we do assume we know the rank, or at least an upper bound on the rank, okay? So then the best solution can only be worth K times this value, okay? Now, as bigger elements come around, new personal bests, I'm going to shift my window of parallel solutions up and get rid of guys who fall too low. So that's okay. And this is all in the KDD paper. Yeah, we didn't try to really get any juice out of 2 passes, but it's worth noting that the Chakrabarty and Kali paper did. They get some improved ratio with like 1 over epsilon passes kind of thing. Right.
Any other questions? All right. In the mountain case, so I saw that everything was at 1/2 for random constraints. Right?
Sorry?
In the mountain case,
Uh-huh.
so in the simple setting, the best algorithm gets 1/2.
Yeah, 1/2.
Do you think this is the correct answer?
Well, there's other relaxations, right? So particular, I think randomizing the order can get you more juice. And just even a little more space. So there will be a talk later this week about distributed, and they'll use square root n space, and they'll break 1/2. Maybe not 1 pass, but as for the exact,
In the random order, if you assume it's random order with the square root, then you can get.
yeah. So this is the right. So with random order and using up the square root n space, I think in 1 pass, you should beat 1/2. It's not easy.